Welcome back, everyone, for another deep dive. You know we love it when you send us stuff to dig into, and you guys have sent in some really interesting stuff about how researchers figure out what causes what, especially when they can't do a straight-up experiment.
Yeah, that's a great point and a really common problem. We're going to be tackling that today, a deep dive into research methods, specifically something kind of propensity score analysis, or PSA for short.
PSA. Got it.
It's a tool that's super important for helping researchers figure out if something really causes something else, even when they're dealing with what we call observational studies.
Additional. Right.
One of the sources you guys sent in was this really great article by Hai and Bai from Educational Psychology Review, which gives a really clear explanation of PSA. So we're going to be diving into that today.
Perfect. So before we get into all the nitty-gritty details, why should our listeners care about this? You know, someone who's just trying to stay informed and learn new things, why is this important for them?
That is the question, right? I think it's important because we encounter so much information every day, from news stories to research studies to even just conversations with friends where people are making claims about what causes something else.
Right.
And understanding how researchers try to figure this stuff out, especially when they can't run a perfect experiment, can really help all of us become more critical thinkers and better able to evaluate the information that's coming at us, separating the good stuff from the not so good stuff.
Yeah, absolutely. I mean, we're bombarded with information all the time, and I feel like everyone has an agenda. So how do we know what to believe? How do we know what's actually true?
Right. And a lot of times in a lot of fields like education, social sciences, even healthcare, you can't always randomly assign people to different groups to test something out. Like, you can imagine why that wouldn't be ethical in certain cases.
Right.
So researchers need other methods to try to isolate the effect of something like a treatment or an intervention. And that's where PSA comes in.
Okay, so let's break it down. What exactly is propensity score analysis?
In the simplest terms I can think of, PSA is like a statistical detective tool that researchers use when they're working with data that comes from observational studies. It helps them estimate the impact of a specific treatment or intervention, even when a randomized controlled trial isn't possible. You know those gold standard experiments where you can randomly assign people to different groups?
All right.
And a lot of the groundwork for this method actually came from two researchers named Rosenbaum and Rubin back in 1983. They did some really groundbreaking work that highlighted PSA as this really important method for making causal inferences when you can't do that ideal randomized controlled trial.
So it's about making those causal claims, but in a different way.
Exactly. So in a randomized trial, you have those nice, neat groups, right?
Yeah.
And you control who gets what. But in observational studies, it's not like that. The groups might already be different in a bunch of ways before the treatment even starts.
Like if you're studying, let's say, a new teaching method.
Perfect example.
The students who end up in the group trying out the new method, they might already be different from the students in the group using the old method. They might be more motivated. They might have better study habits. Who knows?
Exactly. And those pre-existing differences that we call covariates can make it super hard to figure out if it was really the new teaching method that caused any changes or if it was something else about those students.
Right. So PSA swoops in to save the day.
In a way, it tries to. The main idea is to statistically level the playing field between those groups, to try to account for all those differences we can observe and measure.
So it's like you're adjusting for the fact that the groups weren't perfectly matched to begin with.
Precisely.
Okay, so I'm getting the gist of it. But what's the deal with this propensity score? How does that fit into all of this?
So the propensity score is kind of like a prediction for each person in the study. It's the estimated probability or chance that they would end up receiving the treatment,
Okay.
based on all the things we know about them, all those characteristics and background information we've observed and measured.
So it's like you're saying, based on everything we know about this person, how likely were they to end up in this particular group or getting this particular treatment?
Yeah, exactly. And there's even a fancy formula for it that researchers use. It's often written as E of X equals the probability of Z equaling 1, given that X equals X.
We don't have to get into the math here, do we?
No. Don't worry. We won't go full on algebra on you.
Okay, good.
But basically, it's a way to quantify how predisposed someone was to get that treatment based on their individual traits.
So can you give me some real-world examples of those observed traits or covariates, as you call them?
Sure. Let's stick with your teaching method example. So in that case, those covariates could be things like the student's age, their gender, their socioeconomic background, their prior grades in that subject, their learning style, maybe even their motivation levels.
Okay, so anything that you could potentially measure about the students that might be related to both whether they end up trying out that new teaching method and how well they ultimately perform.
Exactly. It's about trying to capture all those pre-existing factors that could influence both the likelihood of getting the treatment and the outcome you're interested in.
Okay, I'm starting to see the bigger picture here. So once the researchers have figured out everyone's propensity score, what do they do with it? What are the steps involved in actually using PSA?
All right, so according to Bai's article and the original work by Rosenbaum and Rubin, there are 4 basic steps to PSA. The first step is all about identifying and measuring as many of those relevant covariates as possible.
So step one is like gather all the data, gather all the information you can about the participants.
Exactly. And this is actually super important because it needs to be guided by a really solid understanding of the research topic. Like, what do we already know from existing theory and previous research in this field? What factors are most likely to influence the outcome we're looking at?
So it's not just about blindly measuring everything. It's about being strategic and thoughtful about which information is actually relevant.
Right, you have to be selective, but also comprehensive. You want to capture all those important differences between the groups that could potentially mess with your results.
Okay, so step one is gather the right data.
Yeah.
Got it. What's next?
Step 2 is where the magic of statistics comes in. Here, researchers actually calculate those propensity scores. And they typically use some pretty fancy statistical models for this, like, logistic regression. Sometimes another method called linear discriminant analysis.
Okay, I'm not a statistician, so you're going to have to break that down for me a bit.
Sure, no problem. So these models essentially take all that data you collected on all those covariates, and then they use that data to predict the probability of each person in the study receiving the treatment.
So for each student in your example, you'd end up with a score that says, okay, this student, based on all the stuff we know about them, had this much of a chance of ending up in the group trying out the new teaching method.
That's exactly right.
Okay, and then what? What do you do with all these scores?
All right, so that brings us to step 3, which is all about using those propensity scores to create groups that are more comparable, statistically speaking.
Right.
And one common way to do this is through matching.
Matching, okay.
So researchers try to find pairs of individuals, one from the treatment group and one from the comparison group, who have very similar propensity scores.
So you're finding a student who got the new teaching method and a student who didn't, but their scores are super close. Like their background and characteristics suggest they were equally likely to end up in either group.
Exactly. And by creating these matched pairs, you're essentially trying to even out those pre-existing differences between the groups. Another approach that researchers sometimes use is stratification.
Stratification, okay.
Right.
That sounds complicated.
It's not as bad as it sounds. It's basically where you divide the entire sample into different subgroups or strata based on ranges of propensity scores.
Okay, so you're like categorizing people based on how likely they were to get the treatment.
Exactly. So instead of pairing individuals, you're creating these groups of people who all had a similar chance of receiving the treatment.
Okay, so you've done all this matching or stratifying. Now what? What's the final step?
Ah, yes. The grand finale. Step 4 is where you actually conduct your main analysis.
To see if the treatment actually had an effect.
Exactly. And you do this either on those matched groups you created or by using some statistical adjustments that take those propensity scores into account.
Okay.
The key here is that by balancing out all those observed pre-existing differences, you can get a much more accurate estimate of the true effect of the treatment. Whether it was really the new teaching method that made a difference.
Wow, so PSA is like this super clever way to try to make sense of messy, real-world data. It's like you're trying to recreate the conditions of a randomized controlled trial, even though you couldn't actually do one.
Yeah, that's a great way to think about it. And that's one of the big reasons why researchers really like using PSA when a randomized trial just isn't possible, for practical reasons or ethical reasons.
Makes sense.
Yeah.
So it's not a perfect substitute for a true experiment, but in a lot of cases, it's the best tool we've got.
Exactly. As Glenn and some of his colleagues have written, there are a lot of situations where PSA is the best option. Like, for example, Gunn and Rosenbaum found that propensity score matching often does a much better job at balancing out lots of different characteristics at the same time compared to older matching techniques.
So it's like a more sophisticated and powerful way to make sure you're comparing apples to apples.
Precisely. It gets you closer to that ideal balance you'd have in a randomized trial. And Rubin himself considered PSA a really valuable tool, especially when you have tons of data.
Makes sense. The more data you have, the better the model's going to be.
Right. And it's been shown to be pretty robust, even when the way people end up in the treatment or comparison groups isn't totally random.
Like if there's some bias in how people were selected?
Yeah, exactly. A researcher named Heckman and his team did some research on that, and Bai's article also mentions that PSA can even help us figure out if the treatment works differently for people who are more likely to get it in the first place compared to those who are less likely.
Well, that's interesting. Like if the new teaching method was more effective for certain types of students than others.
Right, and that's something Kurth and his collaborators looked at. So it can really get into some pretty nuanced questions. But here's the
Hmm.
thing.
Right.
All of this hinges on one really important assumption, and it's called strongly ignorable treatment assignment.
Strongly ignorable treatment assignment. That's a mouthful.
It is. It basically means that once we've accounted for all those observed characteristics, we have to assume that whether someone actually got the treatment or not is independent of what their outcome would have been if they hadn't received the treatment.
Okay, so I'm trying to wrap my head around that. Are you saying that after you've considered all the factors you've measured, there's no other hidden factor that's secretly influencing both who gets the treatment and what the outcome is?
Exactly. It's like saying, if we did a perfect job of measuring all the important stuff, then the reason someone ended up getting the treatment or not is totally unrelated to what their outcome would have been anyway.
Like in the teaching method example, it would mean that after considering all those factors we talked about,
Yeah.
there's no other hidden characteristic like maybe some kind of underlying learning disability that we didn't measure that's both affecting whether the student got the new teaching method and how they performed.
You got it. That's a great example. And if that assumption holds true, then PSA can give us a lot more confidence in our estimates of the treatment effect. You know that it's not just some random fluke.
Right. It's like saying we've done our due diligence, we've considered all the possible confounders, and we're pretty sure that the effect we're seeing is really due to the treatment.
Exactly. Like Imai and Van Dyke put it under this assumption we have a better chance of getting unbiased estimates, estimates that aren't skewed in one direction or another.
Okay, so strongly ignorable treatment assignment is a big if.
Yeah, it is. It's a really important assumption. And it leads us right into the limitations of PSA. Because if that assumption doesn't hold true, if we haven't observed and measured everything that's important, then PSA can't give us the right answer.
Right. So let's talk about those limitations. What are the main weaknesses of PSA?
So as Agbro and his colleagues wrote, PSA is not a magical solution to all our causal inference problems. There are three main limitations that we need to keep in mind.
Three.
And the first one, and maybe the most important, is the problem of what we call hidden bias.
Hidden bias. What's that?
So remember how we talked about all those observed covariates? The stuff we can actually measure? Well, hidden bias is all about the stuff we can't measure. The unobserved covariates.
The lurking variables that are out there messing with our results.
Exactly. And PSA can only account for the things we've actually observed and measured. So if there are other factors that are influencing both who gets the treatment and the outcome, and we haven't included them in our analysis, PSA can't adjust for that. It's just blind to it.
So it's like you're trying to solve a puzzle, but you're missing some of the pieces.
Yeah, that's a great analogy. And those missing pieces can really mess with your perception of the whole picture.
Right. It could make you think the puzzle looks one way when in reality it's totally different.
Exactly. And this is something that Jaffia and Rosenbaum, as well as Rubin himself, have all emphasized. It's this fundamental limitation of PSA. It can only deal with what it can see.
Okay, so that's hidden bias. What's the second limitation?
The second one is all about sample size. PSA tends to work best when you have a lot of data, a really big sample size.
That makes sense. More data, more power.
Right. But in smaller studies, you might run into a problem where there's just not enough overlap in the propensity scores between the treatment and comparison groups.
So you're trying to match people up, but you just can't find enough good matches.
Exactly. And what happens then is that you have to exclude a lot of participants from your analysis, because you can't find a good match for them. And that leaves you with a much smaller sample to work with.
So you start with a small sample, and then it gets even smaller.
Right, and that smaller sample might not be representative of the population you're interested in, so your findings might not generalize very well. And Rubin actually pointed this out. And Weitzen and his colleagues have also talked about this issue.
Okay, so big samples are better for PSA.
Okay.
What's the third limitation?
The third limitation is a bit more subtle. It's about how we choose which covariates to include in the model.
Okay, so this is getting into that idea of being strategic about what you measure.
Exactly. So remember, propensity scores are all about predicting the likelihood of getting the treatment. But ultimately, what we're interested in is the outcome. Like, did the new teaching method actually improve student learning? And Rubin and Thomas made this really important point that if we include covariates that are related to the treatment but not related to the outcome, it can actually make our results less accurate.
Okay, I'm going to need you to explain that one a bit more.
Right.
Why would including more information make things less accurate?
So it's like this. Imagine you're trying to compare two groups of students on their test scores, and you include a covariate like whether they prefer to study in the morning or the evening.
Okay.
Now, let's say that preference actually has nothing to do with how well they perform on the test. It's just a random preference.
Okay.
But if you include it in your model, it can muddy the waters. It can make it harder to see the true effect of the teaching method because you're now trying to balance out this irrelevant factor that's just adding noise to your data.
So it's like you're focusing on something that doesn't matter, and it's distracting you from the stuff that does matter.
Precisely. It's like trying to find a needle in a haystack, but you keep adding more hay to the stack.
Okay, so the takeaway here is that you have to be really careful about which variables you include.
Exactly. You want to include the stuff that's relevant to both the treatment and the outcome and leave out the stuff that's just going to create confusion.
Makes sense. So we've talked about the strengths of PSA, and we've talked about the limitations. But ultimately, researchers still use it a lot, right? So how do they deal with those limitations? What are some strategies for making stronger causal claims when using PSA?
Yeah, you're right. PSA is still a really widely used method, and there are definitely ways to address those limitations. So first, let's tackle the problem of hidden bias. One of the most important things researchers can do is to conduct something called sensitivity analysis.
Sensitivity analysis. Okay, what's that?
It's basically a way of testing how much your results would change if there were unobserved factors that you didn't measure. You know, those hidden biases we talked about?
Okay, so you're kind of playing devil's advocate. You're saying, okay, what if there's something else going on that we don't know about?
Yeah.
How much would that affect our findings?
Exactly. And researchers like Caliendo and Koenig and Lechner have written about different ways to do this. It's all about trying to figure out how robust your findings are to different possibilities.
So it's like you're trying to poke holes in your own argument to see if it still holds up.
Right. Another thing researchers can do is to test out different sets of observed variables, run their analysis with different combinations of covariates to see if the results stay consistent.
Okay, so it's about seeing if your findings hold true even when you change things up a bit.
Exactly. And that's something Guo and Michalopoulos have suggested. And if your findings are super sensitive to small changes in the model, or if the sensitivity analysis suggests that hidden bias could be a big problem, then you need to be a lot more cautious about making strong causal claims.
So it's like you're saying, hold on, we might not have the whole picture here.
Right, maybe there's something else going on that we haven't accounted for. And in those cases, researchers might need to consider using different methods or combining PSA with other techniques to try to get a more complete picture.
Okay, so that's how you deal with hidden bias. What about choosing the right covariates? Any tips for that?
Yeah, that's a really crucial part of the process. And Rubin and Thomas actually suggested that including a few irrelevant covariates might not be a huge deal if you have a decent amount of data. But researchers still need to be really thoughtful about this.
Right.
They should be guided by the existing knowledge in their field. Like, what do we already know about the relationship between these variables? What have other studies found? What does theory suggest?
So it's about using your expertise to make informed decisions about what to include.
Exactly. And that's something Whiteson and his colleagues have also written about. It's this idea of the researcher's responsibility to use their judgment.
Right. It's not just about blindly following a recipe. It's about understanding the nuances of your research question.
Right. And Bai's article also makes a really good point about transparency. It's super important for researchers to clearly explain how they chose their variables when they publish their findings.
So other researchers can evaluate their decisions.
Exactly. It's about being open and honest about your methods. And unfortunately, Whiteson and others like Burkhart and Greenland have pointed out that this information is often missing from research reports.
Really?
Yeah, it's kind of surprising how often that happens. But it makes it really hard for others to judge whether the PSA was done appropriately. So transparency is key.
Makes sense. The more information you share, the more credible your findings are going to be.
Exactly. And the best practice is to choose your covariates based on a solid theoretical understanding of the topic. And you want to look at what previous research has already identified as important confounding factors. Those variables that are likely to be related to both the treatment and the outcome.
Right. So it's about building on what we already know.
Exactly. And researchers like Dehejia and Waba and Hirano and his colleagues have all emphasized this point. And if there are important factors that just can't be measured, researchers need to acknowledge that as a limitation when they're interpreting their results.
Right. It's about being honest about the constraints of your study.
Exactly. And another really important point is that the way you actually build your statistical model to estimate those propensity scores can also make a big difference. There are lots of different methods and approaches, and choosing the right one can really affect how well you're able to reduce bias. Like, for example, Sapita and his collaborators have written about different criteria that you can use in logistic regression. So there's a lot of nuance to this.
So PSA is a powerful tool,
Mhm.
but requires researchers to really know what they're doing. It's not just a plug-and-play solution.
Yeah, that's a really great point. It takes a lot of careful planning, careful execution, and careful interpretation. And ultimately, Sturmer and his colleagues made this point that PSA should be seen as one tool among many that we can use to try to deal with confounding variables in observational studies. It's not a magic bullet. It's not always the right choice.
Right. It's about choosing the right tool for the job.
Exactly. And Rubin himself famously said that if you want to be confident in causal conclusions from observational studies, you need to see how well those conclusions align with other evidence. It's about building a strong case. And Guo and his colleagues also remind us that we should always be aware of the limitations of our data and our methods when we're interpreting our findings.
Right. Humility is important in science.
Absolutely.
Yeah.
We never have all the answers.
So what's the main message here for our listeners? Someone who's just trying to make sense of all the research out there, all the claims about what causes what. What should they take away from all of this?
I think the key takeaway is that PSA is a really valuable tool for trying to understand cause and effect when we can't do randomized controlled trials. It's a way to try to make those apples-to-apples comparisons that we talked about.
Right.
But it's super important to remember that it has limitations.
Right. Like that hidden bias issue we talked about.
Exactly. And researchers need to be super careful and thoughtful about how they use it, how they choose their variables, how they interpret their findings, and they need to be transparent about the limitations of their analysis.
So it's like a warning sign for us as consumers of research to be a little bit skeptical when we see causal claims based on observational data.
Yeah, I think that's fair.
Like, we should be asking ourselves, did the researchers really consider all the possible confounders? Did they have enough data to make these claims?
Mm.
How do they choose which variables to include in their model?
Those are all great questions to be asking.
And hopefully this deep dive has given everyone a good foundation for understanding what PSA is and how it works. So next time you see it mentioned in a research article, you'll have a better sense of what it means and what to look for.
Yeah, absolutely. And if you're interested in learning more, there are tons of great resources out there. Like, you could check out some of the articles we mentioned today, or you could look for examples of PSA being used in fields that you're particularly interested in.
Always good to keep learning, right?
Absolutely.
Well, thanks for joining us for this deep dive. And as always, keep those critical thinking skills sharp.
And keep sending us your questions and your interesting research articles. We love diving into this stuff with you.
We do. Until next time, happy learning, everyone.
See you next time.